Hello, welcome to week 2 of social network analysis. This week we'll be focusing on modeling social networks. Now, why would you want to model social networks? Just last week we showed how you can learn many interesting things just by analyzing the network structure of real-world networks. What good is a model? Well, a model is going to be a simple representation of that real-world complex network, and it's going to allow you to test certain assumptions, because in order to formulate your model, you have to implement those assumptions and see whether the network that is generated from your model in any way resembles the real-world network that you're seeing. So for example, if you were looking at a social network and you discovered that some people had many more friends than others, well, you could say, oh, well, I think that what's leading to this is just a random fluctuation. So people meet and form edges at random, and some people are going to have more edges and some people are going to have fewer edges. And that's my model. It's going to be a completely random graph model. Well, what happens next is that you can test this. You can generate networks according to your model and see if indeed you get some individuals who have many more friends than others. If this doesn't happen, if your model can't reproduce the distribution of degrees that you see in the real network, well, that means that your model needs to be adjusted, that the way you're thinking about the world and the way that friendship formation functions is actually not what you thought. Your model needs to be extended. These kinds of models also often just serve as a straw man, right? So you know that the model, it's not realistic, right? People don't just meet at random, but you'd like to know exactly how your network is different from such a random network, and that gives you further insight about the measurements that you're taking on your real-world network. Because if your real-world network is looking very similar to say a random graph model, then you can say there's not much interesting going on here. But if it looks very different, if the numbers you get from the model versus the numbers you get in your real network are very divergent, then you can say, aha, this is an interesting feature of my real-world network, and that is what I will pursue further. This very basic network model was first formulated by Erdős and Renyi. They're two Hungarian mathematicians. Erdős was an eccentric. He was very, very productive. He traveled from conference to conference, from one collaborator's door to the next, saying, my mind is open, let's write some papers. And after he would finish the papers, he would move on to the next place. There's actually a network of co-authors that it's prestigious to be close to Erdős in. So if you have an Erdős number of 1, it means you're one of his many, many direct collaborators. If you have an Erdős number of 2, it means you're a collaborator of a collaborator. And so people like to calculate their Erdős number. Mine is 4, by the way, which isn't impressive at all. He collaborated a lot with Renyi, who is actually credited with the quote, mathematicians are just machines who turn coffee into theorems. He and Erdős were very productive, and among their 32 publications are several well-known ones on the Erdős and Renyi random graph model, where they could exactly derive a lot of results about precisely this model of a network where you connect nodes at random. There are basically very few assumptions here. Besides the size of the network, the number of nodes, you just have the probability that any two nodes are connected. This is the probability P. An alternative formulation is that you determine the total number of edges M. And the mathematical treatment is a little bit more difficult in the second case, and in any case the two formulations become very similar once the network is large. So we'll focus on the first one, where you're just fixing the probability that any two nodes are connected. What do these networks look like? Here I've laid out the nodes on a circle, I think it's 20 nodes, and I've added some edges at random. As we learned last week, sometimes the layout is more effective if nodes that are directly connected are close to each other in the layout. So I applied a Spring layout algorithm and got this very typical shape of an Erdős-Rényi random graph. The first thing that we can derive for the Erdős-Rényi random graph is its degree distribution. This tells us how many nodes in the network have no neighbors, how many of them have one neighbor, how many of them have two neighbors, etc. It's going to get a little bit mathematical, but if you've ever had basic probability and statistics, you recognize the binomial distribution. This is all it is. And if you've never had this level of math, don't worry. It's not what I'm going to say. You can also build just through intuition and through playing with the demos. So it's not that you have to derive the binomial distribution from scratch or anything like that. I'm bringing it in more just to show, hey, if you're a mathematician, there's a whole lot of interesting things and properties you can derive about networks. And actually, I'm just going to be scratching the surface of that. So that is the goal, to illustrate how you can intuit some properties when you have a nice model of the network. So again, our model is we have n nodes, and with probability p, we add an edge between every pair of nodes. So we're kind of flipping a coin, right? So one node out of the n is going to look at the n minus 1 other nodes, and for each one it's going to flip a coin to see whether they're going to share an edge or not. Now, to test your understanding, I'd like you to imagine a network, and you're keeping the probability that any two nodes are connected, the value p, you're holding constant, and you're increasing the size of the network, the number of nodes. I want you to think about what happens to the average degree. How many other nodes on average is a node connected to? To help you with this, I have created a NetLogo model. So let me just try and get into that model. And what you're going to do is you're going to make sure that this probability or num is set to probability. You're going to have, you're not going to use this number of neighbors. You're going to fix the probability of linking. Here I've just made it 2%, and we're going to start with 100 nodes. So I'm just going to click this Erdős-Rényi button, and maybe I'll let it lay out just to see what it looks like. So let me try that a few more times. And here I see the average degree. Now I'll increase this to maybe 300 and generate another Erdős-Rényi random graph. I'm also going to look at the average degree. I might do that a few more times, and I might increase to almost 1,000 nodes. Again, generating an Erdős-Rényi random graph. Has to work a little bit harder for a larger graph. And then I'm going to, again, look at the average degree. So see if you can understand what's going on in this case. Now that we've seen what these random networks characteristically look like, we can return to the problem of deriving the degree distribution. The degree distribution is just a probability distribution that's going to say the probability that a node has degree 0, meaning no neighbors, is a certain quantity. The probability that it has 1 is this. The probability that it has 2 neighbors, it's something else, etc. So this is our probability distribution, and the probabilities, of course, have to sum to 1. Back to how this might happen if we're doing a little thought experiment, is that each node is looking at the n minus 1 other nodes, and it's flipping a biased coin, which with probability p is going to say link to that particular node, and with probability 1 minus p is going to say not that one. And the distribution that describes this process exactly, the coin flipping, is the binomial distribution. So what we're interested in is, out of n minus 1 tries, what is the probability that k of them are successful? That is, what is the probability that the node will have degree k? And first we need to know the number of different ways that we can choose k nodes out of n minus 1. This is the binomial coefficient times the probability that you succeeded k times, which is p to the k, times the probability that you failed, n minus 1 minus k times, which is 1 minus p to the n minus 1 minus k. So let's do a little bit of comprehension here. So what is the maximum degree that a node can have in a graph that has n nodes? And here we're assuming that the graph is simple, meaning that you can't have multiple edges between two nodes. It's like two people can only have one friendship. They can't have two or three or four friendships between them. So, and this is the kind of graph that Erdős and Renyi modeled, the simple graph. So what is the maximum degree in this case? Let's delve a little bit more into the binomial distribution. For a lot of you, this will be a review of basic probability, but let's do it nonetheless. So imagine that you have an 8-node graph with a probability p of any two nodes being connected. What we'd like to know is what is the probability that any given node is connected to 4 others. And we're going to color those blue, and the 3 nodes that it's not connected to, we're going to color white. First, we need the binomial coefficient, which is going to say what is the number of ways that you can choose 4 out of 7. Well, you can imagine first that you can uniquely identify all the nodes so that it matters whether, A goes first, B goes second, or B goes first, A goes second, right? And there are 7 factorial different ways of making such an ordering, because for the first spot you have 7 choices, for the second spot you have the remaining 6, the third spot you have remaining 5, etc. So this is 7 factorial if you could distinguish all of the nodes separately. But what we're saying is that we're only distinguishing at the level of whether a trial was successful or not. So whether a node is white or blue, which means that the 3 white nodes are just completely swappable. So our 7 factorial is now divided by a 3 factorial in the denominator, which is the number of different arrangements that we now don't distinguish between. Similarly, for the nodes that we did connect to, there are 4 factorial different ways of ordering them, and now we don't care about their particular ordering, so we have another factor of 4 factorial in the denominator. So in general, this binomial coefficient of choosing, for example here, k items out of n minus 1 is going to be n minus 1 factorial in the numerator, k factorial in the denominator, n minus 1 minus k factorial in the denominator as well. And there should be a parentheses around the n minus 1. Sorry about that. So let's test our understanding. What is the number of ways of choosing 2 items out of 5? Now let's get back to the distribution. Imagine that we have a certain way of choosing the k out of n minus 1. So here it's 4 out of 7. For example, if it was white, white, blue, 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 white, blue, what we would have for the probability of that particular event is 1 minus p times 1 minus p times p times p times p times 1 minus p times p, right? So p to the 4th times 1 minus p to the 3rd. And once we don't care about the particular order of white and blue, we add the binomial coefficient back in. So in the end, the binomial distribution tells us that the probability of a particular node having degree 4 in our 8-node probability p graph is 7 choose 4 times p to the 4th times 1 minus p to the 3rd. And that's it. That's how it works. If p is equal to 0.5, you get this very symmetric looking distribution where it's most likely that the node will have degree 3 or 4, but also it could end up with low probability with no neighbors at all or connected to all 7 of the other nodes. If, however, the probability is only 1/10, then you have a distribution that's much more skewed. It's much more likely that a node will be connected to no others, and very unlikely that it would have anything past degree 4. Once you have this distribution, there are well-known properties such as the mean. The mean is going to give us the average degree. From the binomial distribution, we can tell that this average degree z is going to be equal to n minus 1 times p. And in general, if you had an arbitrary degree distribution, the way that you could calculate the mean is you just take the expected value, which is the sum over all the possible outcomes. Here we're interested in the degree x times the probability of x occurring. To test our understanding, let's see what the average degree would be of a graph with 10 nodes where the probability of any two nodes linking is a third. You can similarly compute the variance. For the binomial distribution, the variance, which is just the standard deviation squared, would be n minus 1 times p times 1 minus p. And it's computed in a very similar fashion, so we won't have to do this in any assignments or anything like that. But in general, you have the expected value of x minus the mean squared, which is the definition of variance, is just this quantity summed over all possible values of x times the probability of each particular value that x can take. The binomial distribution gets quite impractical to compute because the binomial coefficient having those factorials in there just can't be computed for very large numbers. So you typically use approximations. So in the limit of p being small, you can use the Poisson distribution. And in the limit of the graph being large, so n is large, you can use the normal distribution. And the way that both the Poisson and normal are going to look for large graphs is that it's going to be a nicely symmetric distribution around the mean value k. Of course, if the probability is very, very low, then the Poisson distribution actually is not symmetric, right? It might be very much hitting up against degree 0 and then going from there. But the main point to take away is that we're not going to be seeing many nodes that have, say, a degree that's many times higher than the average degree. That's something you simply don't see, and this is because this probability drops off exponentially here as you get higher and higher in degree. So the basic insight that we get out of this is that there are no hubs. Hubs in the sense of some nodes that have extremely high connectivity, extremely high degree. You just don't see this. Let's continue learning about how Erdős-Rényi models can be useful and also what some of their limitations are. So previously, we figured out the degree distribution, and we noted that for Erdős-Rényi random graphs, you don't really have hubs, that is, extremely well-connected nodes. What we'll talk about next is the emergence of the giant component in Erdős-Rényi graphs, and also what their average shortest path is. What I'd like you to do is to go to this app, which is a NetLogo app, to look at how the giant component comes about. In this model, when you click Setup, it's just going to start with a number of nodes. So here I've selected 80. Maybe we should up that to 500. Yes, that's a nice number. So we're going to the max. And if you just click on Go Once, you'll be adding edges one by one, and this can take quite a while. So what you'd like to do is just hit the Go button with the little repeat, and that will just continuously add edges. And if this, for whatever reason, is too slow for you, you can turn the layout off for a while. You can turn it back on, or you can accelerate by moving the speed slider as well. And what you're looking for is at what point is the giant component going to start to emerge. So that takes us to the next quiz, which is just what is the average degree of a node in the graph at the point where the giant component emerges. And if you remember from week 1, the giant component is a component that occupies a finite fraction of the graph as the graph grows. So the idea is that even for a very large graph, if you have a significant, well, a fraction of the nodes being connected, then this is the giant component. This is somewhat related to percolation, which is studied in physics. So if you look at a 2D lattice, a percolation problem might be something like this. If this is soil and the gray areas are actually where there's no soil, and so water can go through, the question is at what density of these empty cells, that is, what fraction of all the spots do they need to occupy such that you start seeing the water seeping through. So I'd like you to go to this model as well, and I'll try to find it here. So you can set up a particular value for P. Here we're going to have 25% of the node of the sites occupied, and we can set up the lattice, and here I can tell that it's just too small, right? It doesn't, the water can't percolate through. You can, instead of trying all possible values, you can also systematically vary P from 0 to 1, and so here it is. So what I'd like you to do is to answer the following quiz question, which is just, what is the percolation threshold in a 2D lattice? What fraction of the sites need to be occupied? And this then is related to our problem of the percolation threshold in the random graph, which is just going to tell us at what density of the network, and here we're really talking about, by density in this case we mean the average degree of each node, at what average degree do you start to see a giant component. And in fact, you should have seen that right around degree 1 is when the giant component starts to emerge. At first it's going to look fairly stringy and tree-like, and then over time it's going to look more and more dense, over time meaning that you're adding more and more edges. Another way of looking at this, which is interesting from an epidemiological perspective, is that you want to know how can the disease spread through the network. If people are connected, even if it's through several hops, it means that theoretically the disease could spread from person to person to person. And there's a nice property of the degree distribution because it has an exponential tail, and an exponential distribution will tell you that the average degree of a node that you're connected to, excluding yourself, so how many friends do they have besides you, is the average degree in the network. Now you might say, well, wait a second, how can they have the average number of friends plus me? That's like average number plus 1. Well, the people you're connected to are actually not average. If you think about it, the probability that you're connected to someone who has 3 friends is 3 times as much as the probability of being connected to someone who has just 1 friend. So indeed, your friends do tend to be more popular than average simply because more people know them and you're more likely to be one of those people. And so then when we return to this idea of the giant component and the percolation threshold, what we're really asking is, I have a friend, what is the average number of other people that they know? If it's at least 1 other person on average, then this chain can continue, and we're likely to be part of this giant component through which information or disease, etc., can spread. However, if my friend has fewer than 1 other friend on average, then it's likely that this chain is just going to terminate sooner rather than later. You might be asking, why is there always just 1 giant component? Why can't the network accommodate several? In the Erdős-Rényi random graph and many other networks, the giant component will occupy some fraction of the network that scales linearly with the size of the graph. It means it's some fraction of n. And all the other smaller components will occupy at most some factor times log n nodes. They'll incorporate that many nodes. And the question is, why is this? Well, let's look at the counterexample. What if we have 2 large components? If we were to continue adding edges, how long could they really stay separate before merging into 1 giant component? So what I'd like you to do is to look at this particular NetLogo app with 2 components. And what you'll be doing at first is you're going to keep them separate. So this switch is going to be on, and you can select some number of nodes. 80 is fine. And then we're going to create the nodes, and you're going to have the circles and the squares. And while you're keeping them separate and you're adding edges, say one by one, they're only going to be occurring between the circles and between the squares, right? And so you're going to do this for a while. You can kind of let it evolve, right? And what I'd like you to do then is to flip this switch and then add edges one at a time and see how many edges do you need to add before these components merge. And hopefully that will help with some of the intuition about why we have just one giant component. So this is basically the quiz I'd like you to take, which is tell me how many clicks it took before the components merged. The next thing that we can figure out about our Erdős random graph is the average shortest path. And this is just how many hops on average does it take between any pair of nodes. So here I've circled two nodes in blue, and this is their average shortest path. It takes 3 hops, 1, 2, 3. And we would do this for all pairs of nodes. Now what we want to know is can we use knowledge about the average degree and properties of the Erdős random graph to figure out how the average shortest path should scale with the size of the network? So the calculation that we're going to do, and it's going to be an approximation. It's actually extremely difficult to derive exact relationships for the the exact shortest path for a particular model, but for many of them you can figure out what the general scaling is going to be. So the approach here is that you have a node and it has some number of friends on average. So it might have, say, 2 friends at distance 1, and 4 friends on average at distance 4, and 8 friends on average at distance 3, if the average number of friends is 2. And here I've made each branching point 2, but in general, some friends are going to have 1 other friend and other friends are going to have 3 other friends. And so the basic idea is that at distance L, you're going to have a number of Lth degree friends that's proportional to z to the L. And this makes the scaling of the average shortest path equal to log n over log z. And again, this isn't an exact quantity, but a scaling and approximation. So there's something very cool about this, which is that the graph can grow very, very large, meaning that it has lots and lots of nodes, and yet any 2 nodes are going to be connected through a short number of hops. So here on the x-axis, I've plotted the number of nodes, and on the y-axis we have the average shortest path, and you can see that even as the network gets very large, you get the shortest path growing slowly. It's growing only logarithmically. So let's talk about logarithms for those of you who aren't as familiar about them. As you exponentiate a number, for example with 2, 2 to the 0th power is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. That exponent is what would happen, is basically if you were to take the log base 2 of 8, it would be 3, right? So when you place numbers on a logarithmic axis, what happens is that things that are powers of each other's, so 1 and 10 and 10 and 100 will be equally spaced. And so you'll be able to see exponential and logarithmic relationships between the variables. So if we plot now the number of nodes on the logarithmic axis on the x-axis, what we can see is then a straight line, meaning that this is the growth of the average shortest path. It's something like log n. And so just to quiz you, I'd like to know what happens to the average shortest path in an Erdős-Renyi graph when it when the number of nodes increases 100-fold. So for example, you go from 100 nodes to 10,000 nodes. What will be the proportional change in the average shortest path? The second aspect that I'd like to discuss, in addition to all of the neat things that we can predict with our Erdős-Rényi model, is the question of how realistic it is. We're going to consider some alternative models, alternative ways of generating graphs, and we're going to compare them in a series of little quizzes to what you would see with an equivalent Erdős-Rényi graph. So I would like you to go to this particular NetLogo model. And so let me just go to that model, in fact. Okay, so in this model, you can generate your regular Erdős-Rényi random graph. It's reporting several things back to you. So here's the degree distribution, the size of the giant component, the average degree, and the average shortest path within the giant component. So probably you want to start off with using probabilities, P, instead of the number, which is the average number of neighbors that you want in your network. And you can lay out this network, and there's some parameters you can change. For example, the length of the springs, or the repulsion strength, and even the spring constant, and you can see how all of those work out for you. The main point is just that you see a little bit of the network structure and you can evaluate what the model is doing. Now, the first model that we'll be looking at is the introduction model. In the Erdős-Rényi model, what you have is just nodes forming edges at random. And you might think, well, in a social network, maybe that's not that realistic. Certainly some encounters are random. However, a lot of people we meet through our friends. So keeping the same probability of linking, what I'd like you to do is see as you vary this probability of being introduced to a friend. So if it's 0, it means all of your edges are purely random, so it should look really similar to an Erdős-Rényi graph. However, if you increase this probability, most of the introductions, most of the edges that you get should occur through introductions. And so you may want to compare the structure. So let's see what the quiz asks. This is our model. We want to know, relative to the Erdős-Rényi random graph, whether there's difference in the number of edges, in the number of closed triads, that's these guys, where all 3 people link to each other, the average shortest path, the degree distribution, and the size of the giant component. The next model we'll consider is a static geographical model. So each node is going to try to connect to some number of its closest neighbors. Some nodes may end up with more neighbors simply because a lot of others were close to it and not, but it already had its 3 closest neighbors. And for this one, we'll want to turn off the layout just so we can actually see the geography at work. I'm going to also switch to the num neighbors, determining the density of the graph. And so I'm just going to click on Stat Geo, and it's just highlighting the largest connected component here in red. And what we'd like to know about this one, let's see what our quiz is. We'd like to know, relative to the Erdős-Rényi random graph, whether this kind of static geographically generated graph has longer or shorter average shortest paths, broader or narrower degree distribution, and smaller or larger giant components. So to compare something like that, all you would do is, without changing any other parameters, you would click on Erdős-Rényi to generate an equivalent Erdős-Rényi random graph, and then you would look at the size of its giant component, average degree, average shortest path, to contrast with the other model. So going back, the next one that we will consider is the random encounter model. This is somewhat similar to the static geographic model, except that it's not static. So people move around, but those encounters have to do with whether they were proximate to other people. In fact, if they kind of bump into each other, it's when they form an edge, and then they can kind of like wander around from there, but they still retain that edge. And again, we want to compare with the Erdős-Rényi random graph. So for this, I also want to at least initially turn off the layout function. I'm going to click on random encounter and see, for example, if the number of neighbors is 2, what does the resulting structure look like? I can apply the layout algorithm, and I want to, for this one, you may want to see what happens if you have an average degree of 3, right? And we want to look at this network relative to the equivalent Erdős-Rényi, right? And so again, we want to answer very similar questions about, are there more or fewer closed triads? Is there a smaller or a larger giant component relative to the Erdős-Rényi? The next model we'll look at is a growth model. Here, instead of having all the nodes present up front as we do with the Erdős-Rényi model, we're going to be adding them over time, just intermittently along with the edges that are being added. So you might ask, well, okay, what does that mean? Nodes that have been around longer, do they get more edges? We shall see. So in the growth model, you're just clicking, I won't switch to the model. Well, I guess I might as well, okay. So you just click on growth, and you're going to be similarly looking for things such as the presence or absence of hubs. So again, looking at the degree distribution, and also looking at the size of the giant component relative to the Erdős-Rényi random graph. What we've learned from these other models, I hope, is that in some instances the Erdős-Rényi model might be plausible and it might match these other dynamics. So maybe the size of the giant component wasn't that different, maybe the degree distribution was similar. However, sometimes these different dynamics actually led to different graph properties. And so what we'll look at next is some alternative models more formally that can explain some of the things such as degree distributions observed in real-world networks that don't quite match the Erdős-Rényi binomial degree distribution. So far, we've discussed how networks might grow in ways that differ from the Erdős-Rényi random graph. What I'd like to talk about next is how growth, specifically in networks, can lead to some of the skewed degree distributions that we see in real-world networks. Here's an example of one such network. It's the Java Forum, an online question and answer forum that my collaborators and I explored to see if we could automatically identify experts. It turned out that identifying the experts was super simple. All we had to do was look for people who had replied to lots of others, and these indeed ended up being the most expert users as evaluated by humans who are actually reading their replies. Here I've also colored the nodes by whether they have an edge to another person because they replied to their question or because they posted a question and received the reply. So the repliers are colored in red and the askers are colored in blue. We can look at the degree distribution and see that it's highly skewed. It's more skewed in the case of the repliers because you see that some repliers have replied to upwards of 1,000 other users, but it's rare for an individual to have received replies from more than a couple of dozen different helpers. In this case, the distribution that I've plotted is the cumulative degree distribution. And this means that we're not looking at the probability that you had interacted with exactly k other people, but k or fewer other people. In any case, we do see some deviation from a straight line, but overall, especially for the repliers, we see a very high skew. This isn't the only instance of seeing a very highly skewed degree distribution. Another example is the network of human sexual contacts. And even though men do tend to report having had more partners than women do, in both cases the degree distribution for both men and women is highly skewed. And this has interesting implications, for example, for the spread of sexually transmitted diseases. Now, in a little while, like next week, we'll focus more on identifying the true power laws from the fakes. But for now, let's just assume that we're seeing a true power law distribution. The way that we're going to recognize it is that we're going to have a straight line on a log-log plot. Now, if we had plotted the same power law distribution on a linear scale, we would hardly even see it. We would see this very sharp drop off, basically like an L shape, and we wouldn't be able to tell whether a node had any chance of having degree 40 when most other nodes have degree 1. But if we look at the log-log scale, we can see that even though it's not very likely, just a fraction of a percent, that someone would have degree 40, it's not negligible. And in fact, this is what is called a heavy tail. That is, the probability drops, but it doesn't drop exponentially. It doesn't do this. Instead, it keeps going decade after decade. We can contrast this with the Poisson distribution, which, if you remember, this is the distribution that describes the degrees in an Erdős-Rényi random graph. Here I've even been generous and I made the average degree be 10. And now we might ask the same question: what is the probability that someone has degree 40? Well, on the linear scale, it looks 0, like it did for the power law distribution. But if we now plot on a log-log scale and we look around 40, we see that that probability is actually very small, something like 10 to the minus 10, and by the time you're over 50, right, this is 10 to the minus 64, so this is actually 100. There's no chance that someone would have degree 100, no matter how large the network is, if it's an Erdős-Rényi random graph with an average degree of 10. So there's a very stark contrast between the Poisson distribution of the Erdős-Rényi and the power law distribution that we see in many real-world networks. So let's look at this power law distribution. What we saw essentially was a line on a log-log plot, which means that the log of the probability of having degree k is equal to some constant minus alpha, this is our power law exponent, times the log of the degree k. And so if we exponentiate both sides, we get the probability of having degree k is equal to another constant times the degree k to the minus alpha. So let's check if we understand what's going on. As the exponent alpha increases, so this, we're not talking about minus alpha, we're talking about the exponent alpha, the downward slope of the line on a log-log plot, what does it do? Does it stay the same, become milder? So from your point of view, does it do this? Or does it become steeper? Does it do this? Given that many real-world networks seem to display power law degree distributions, what we'd like to do is come up with a network model that can produce these distributions as well. And for this, we're going to need two ingredients. The first of which is that the network grows over time. So as time goes on, you have more and more nodes added to the network and more edges. There are many networks for which this seems plausible. For example, if you look at citation networks, when a new paper is written, it will cite papers that have come before it. Although social networks are not power law, and this is not so much that people don't want to connect to very popular people, but practically speaking, we can't keep up in a meaningful way with thousands or tens of thousands of friends. So even though social networks are not power law, you can imagine a similar dynamic where individuals join the network over time, whether through birth or another process that they land in a given social network, and then they're going to start forming edges to other individuals within that network. There's going to be a second component, which is that when you come into the network, you're going to have some edges that are allocated. For example, if you're a new paper, you're going to have, say, 30 or 100 or who knows how many citations that you're going to give to the papers that have come before you. So in the social network context, what you're deciding between, or I guess let's stick to the papers. In the papers context, what you're deciding between is citing a paper that no one else has cited or citing a paper that lots of other people have cited. In the social network context, you might be deciding between connecting to someone who doesn't have many, if any other connections, or connecting to someone who's popular and has lots of social ties. And if you prefer the person who has lots of social ties, in fact, if you prefer him in or her in proportion to the number of ties that they have, then this is called preferential attachment or cumulative advantage. Let's first look at the first factor, which is that the network is growing. So here I've used NetLogo to grow a network where each new node comes in with 2 edges that it allocates. So you can see that some nodes have more edges than others, but it's still relatively evenly distributed. The edges are between the nodes. We can derive some properties of the degree distribution here, and in order to do this, we're just going to look at what's going on. And what's going on is that at each time step, you have one new node coming in with m edges to allocate, which means that at time step t, you're going to have t nodes. Now let's look at a node that's born at time I, and we'll call its degree k sub I. We know that k sub I on average is going to be changing at a rate of m over t. Why m over t? Well, at each time step a new node comes in and it has m edges to give, but it's going to allocate them among the t nodes that are already there, so each individual node is competing with those t others for the m edges. We can then see what happens, over the lifetime of that node, since time I when it was born to time t, how many edges do we expect that it has? So we integrate the change in its degree from I to t, and we add the m edges that it had up front. And this is just the k sub I t is equal to m plus m log t over I. From this, we can see that on average, nodes that were born earlier are going to have more edges than nodes that are born later. They've simply been around longer and have been accumulating and accumulating these edges. What I'd like you to think about is in which ways this is realistic or not. So if you think about social networks, what other modifications to the model might you make in order to make it more realistic? Okay, back to our very simple model though, with no modifications. We just have nodes arriving over time. Now we want to derive the degree distribution, and for this we're going to be using the fact that nodes that are born later are going to have lower degree on average. So for example, if we want to know what is the probability that a node has degree 100 or less, we're going to figure out at what time a node with average degree 100 was born. We'll call that time tau, and then the fraction of nodes that have lower degree are just going to be the ones who are born after it. So this is t minus tau over t is that fraction. And we have the solution for the degree of a node that was born at time tau from before. So we're just going to solve for tau from this equation and derive an exponential distribution for the degree of the nodes. So given that this is an exponential distribution, what I'd like you to answer is, what do you expect this degree distribution to look like on a log-log plot? Is it going to be a curved line, or is it going to be a straight line? The second ingredient we need is that of preferential attachment. That is, when the new nodes come in, they're not going to just connect to any node at random. They're going to prefer some over others, and in fact the ones that they're going to prefer are the ones that already have a lot of edges. This kind of process is also known as a cumulative advantage process, a rich get richer phenomenon, or the Matthew effect. That is, those nodes who already have a lot of edges are going to get even more disproportionately. In fact, it's going to be proportional to the number of edges that they already have. The first such model proposed for networks was proposed by Price for citation networks. In his model, you have papers coming in, and each paper is going to cite m other papers on average. But instead of just citing any old paper it can find, it's going to cite other papers in proportion to the number of citations the paper already receives plus one. That plus one is a little trick to make the model work because a lot of papers start out with no citations at all. So if you were citing in proportion to the number of citations, you'd have a cold start problem. So this kind of helps the process along. The process generates a very nice degree distribution, which has a power law exponent with alpha equal to 2 plus 1 over m. A lot of the real-world citation networks do have power law exponents slightly above 2. So it's just a very nice match and a very nice description of reality where a few papers get lots and lots of citations, thousands, tens of thousands. But most papers are relatively neglected. They get no citations at all or just a couple. You might think, well, preferential attachment makes sense for social networks. If this little node is coming in and he's saying, well, who's going to be a good friend to have? Well, the person who has no friends, well, they can't introduce me to anyone else. Maybe they're not such a good friend to have, but this person here, oh, they're so popular, let me connect to them. Now, how does this translate to papers? Why would you want to cite papers that are already well cited? Well, you know, for one, they're probably better, but there's also a lot of anecdotal evidence that it's a little bit of a luck of the draw, right? You can have two scientists making pretty much the same discovery, but one paper gets a lot of attention and the other one is relatively unknown. So how can this happen? Well, one way in which it happens is through a copying mechanism. So when I'm reading a paper that I think is relevant to my research, I'm going to look at the references and the papers that it cites, and then I might copy one of those references after I read it, of course, right? I might copy that into my own paper. And if you think about it, the chance that I encounter a citation to a paper is proportional to the number of papers who cite it. Now, there could be other mechanisms. For example, the better cited a paper is, the more likely it is that the authors are invited to give talks, which in turn means that more people find out about the paper, etc., etc. So that's one possible preferential attachment mechanism. Now, what really set off a lot of research in complex networks was the model proposed by Barabási and Albert, which is similar to the Price model but not quite. And what they were aiming to do was to describe why there's a power law distribution in the number of inlinks that different web pages receive. So in their model, you have new web pages arriving over time, and they're each going to link with m links on average to web pages that are already there. And the probability of linking to an existing page is going to be proportional to the number of other pages that are already linked to that page. And so this probability here that a given new node is going to connect to node I is going to be equal to m, which is the number of new links it has to add, the degree of node I over the sum of the degrees of all the other nodes. And this results in a power law exponent of 3, which is a little bit problematic because the web degree distributions are much closer to 2, and 3 is a relatively steep power law exponent, meaning that you don't get the most popular websites would not be as popular as you would see in the real world. So but you can correct for this in various ways, and Barabási and Albert did indeed do this later by introducing different fitness for different sites, meaning that some sites are just a little bit more interesting, and so they get more links. But let's see how this model works. So if we were to simulate it, we would start, say, with a connected component of 3 nodes who all link to each other, and now we're going to add new nodes one by one, but we want to keep track of the degree of each node, and so for each edge we're going to record the endpoints and enter them into a flat list, And then when a new node comes in, so say 4 comes in, it's going to choose from this list of 1, 1, 2, 2, 3, 3. But now if it happens to choose 3, now 3 has degree 3 and is represented 3 times. And so now when 5 comes in, it's a little bit more likely that it's going to choose 3 as well over 1 or 2. Or actually over 1, which only has degree 1 still. So that's the basic mechanism, and I've implemented it in NetLogo as well, so you'll get to play with that. After a while in NetLogo, what you see is a network such as this one, where hopefully when you compare it with the purely random growth model, you're seeing bigger hubs emerging relative to here. With the random growth, you have the older nodes are accumulating more links, but not nearly in kind of a skewed fashion as is happening in the preferential attachment model. We can also examine this analytically, as Barabashi and Albert did. So again, we're just looking at how the degree of a node I changes over time, and we've already specified this. So at each time step there are m new links going around, and they're going to be allocated in proportion to the degree of the node divided by the sum of the degrees, and here it's just t times m edges, and you have 2 endpoints for each edge, so it's just t times m times 2. And what we'll see again is that if we want to figure out what the probability is that a node has degree, say, k prime or less, what we want to figure out is at what time point tau was the node with average degree k prime born, and then we know that everyone born after that will on average have had lower degree. And so following a similar derivation, we have this distribution that says the probability that a node has degree k is 2m squared over k to the third. So this is your power law exponent of 3. So besides this nice power law distribution, other properties of this network, which this one actually holds for the growth model as well, is that it's just a single connected component. And this is simply due to the mechanism, which is that we're adding a node at a time, and it's linking to the nodes that are already there, who link to the nodes that are already there, and so everything ends up being connected. If you remember, we also looked at a growth model where new nodes were being added, but the new edges were not necessarily coming from the new node. And in that case, of course, you don't necessarily get everyone in the same component. So for some graphs, it might make sense. So for example, for web pages, you might assume that maybe the links are only added when the web page is created and they're not added after the fact. But for other networks, it might make more sense, you know, if you have a social network, maybe initially a person who's come to a new city doesn't know anyone, but they get to know someone, and then they get to know more people. So it really depends, right? For citation networks, this seems to be a very appropriate model. And the final observation, which is also consistent with the random growth model, is that again you have the older nodes having more edges, and the newer nodes, the youngins, actually don't really have a chance to catch up because they're born much later, and so they're born with you know, when they're born, they have very few edges. The older nodes have been around longer, and some of them have gotten really big, so they're going to continue to accumulate. So if we look at these two nodes, this one was born at time equals 5, and this one's born at time equals 95. And so you can see that they're both kind of tracking in terms of their growth, and since this is a log scale, really at the point that the older node has over 100 edges, this younger node just has a few dozen, right? And it's not really catching up. So you'll have the opportunity to try this yourself. So let me see if I can switch to the model. Not this one. This one, not this one. Okay, please be this one. Okay, great. So sorry about that. So here in this model, you can use preferential attachments. So let me do that. So hopefully you'll observe lots of hubs here. Now if we have the probability of preferential attachment be 0, and you can use anything in between as well. So we're going to set this up. And so it might seem similar at first, but the thing to do is to look at the degree distribution and also look at the size of the nodes to see if you can spot the difference in the two networks. Again, they're both growing, but one has preferential attachment and the other one does not. So just to test your understanding, relative to the random growth model, the degree distribution in the preferential attachment model is going to resemble a power law distribution less or more. So just to summarize the growth models, the reason for doing growth models is that most networks aren't born, they're made. They grow over time, and this means that some nodes, the older nodes, might accumulate more than others, but if you have this additional ingredient of preferential attachment, then nodes that for whatever reason end up with more edges as the network grows are going to accumulate even more edges at the expense of other less fortunate nodes. Now, for the assignment this week, what you'll be doing is looking at the implications of these models for diffusion. And so even if you're mostly just listening to the lectures, I think that, doing this assignment will be, it'll be a cinch, and it'll be interactive. In the sense that you'll be playing with these NetLogo apps. So I encourage you to do it even if you don't turn in the assignment. I think it'll be worthwhile. So the one part of it will be looking at, and let's see if this is the case. Oh, nope. It'll be looking at the Erdős-Rényi random graph, and here you'll be looking at what does it mean to have a giant component that doesn't occupy the whole network for how disease is going to spread. So you're going to have one node infected, and then that one node is going to start infecting others, and then those nodes are going to infect others in turn, and you'll see what happens. And in another part, you'll be looking at how quickly information or disease or other things can spread on the network depending on whether the network grows randomly or grows with preferential attachment. So hopefully it's this one. Okay, great. So you'll be setting up your network, and here it's not preferential attachment, and then you're going to start spreading, and you're going to see how long it takes for the information or disease or whatever to spread. So I hope that'll be fun, and this is the end of week 2. Thanks. Welcome to week 2 of social network analysis. This is the less mathy version of network modeling. Why do we want to model networks? Because we want to understand the underlying dynamics that lead to the observed structures. So for example, last week we looked at several networks and observed some interesting characteristics. We thought we understood how girls in a dormitory choose their dining table partners. However, knowing particular values that we measure for one network does not mean that if we go to another dorm, we can predict what those values will be for the other setting. But if we have an underlying model that tells us, well, these are the motivations for the edge formation in that network, then we may very well be able to generalize and make predictions about networks we haven't even yet observed. This is all nice, assuming that your model is actually a good representation. Now, how can you tell that your model is valid? Well, what you're going to do is you're going to generate either through simulation, which is what we'll be doing with NetLogo, or you can derive mathematically properties of networks that follow the dynamics and the assumptions that you make in the model. And if those values agree, if your prediction based on the model agrees with the observed quantities, then your model is a good one. However, if your model fails to predict some features, then you know that perhaps there's room for improvement. Maybe there are additional characteristics that need to be incorporated into the model. So for example, if in the dining table partner networks that you observe, you see that some girls have many more incoming edges than others. If your model is that partners are chosen at random, you may or may not be able to reproduce that observed degree distribution of some girls having much higher degree than others. So in that case, you may need to incorporate additional features into your model. For example, that some girls are intrinsically more desirable as dining table partners than others are. Or there may be other mechanisms that can lead to this discrepancy or dispersion in the degree distribution. And we will talk about some of those models this week. First, let's talk about the most essential model of networks, and this is the Erdos-Renyi random graph. First, let me tell you about Erdos and Renyi. Erdos is a very famous mathematician who was extremely prolific, wrote, I think, hundreds of papers. And the way in which he wrote them was he would travel from one mathematician's doorstep to the next. And when he arrived, he would say, "My mind is open. Let's work together." And after writing a paper or two with that person, he would then go on to the next. And this, as you might imagine, meant that in the co-authorship network, Erdos had an extremely high degree. And in fact, if you look at the whole network, it's a matter of prestige what your Erdos number is. Your Erdos number is 1 if you directly co-authored with Erdos. It's 2 if you co-authored with someone who then co-authored with Erdos, 3, etc. Mine incidentally is 4, and there are lots and lots of people who have an Erdos number of 4. It's not a very prestigious number at all. But by being so productive, actually Erdos ends up being the center of this very large network. Now, one of his favorite collaborators is Renyi. Renyi is credited with the quote that mathematicians are machines who turn coffee into theorems. Together, they wrote a series of papers on the properties of the random graph, which in this course and in general is called an Erdos-Renyi random graph. Now, let's look at what the assumptions of this model are. They're very few. It's just going to be that the nodes are going to connect at random, so any two nodes in the network are equally likely to connect. The network is going to be undirected, so unlike the dining table partners where you had one girl picking another as her favorite, but this not being reciprocated, here the edges are undirected. And the last assumption, or the last parameter, is what the probability is of any two nodes connecting. We'll call this probability P. So for example, any two individuals might have a probability of 0.1 of having an edge, meaning that 1 out of 10 edges that could exist in the network actually do. Alternatively, what you can do is specify the total number of edges in the network. We'll call this M, and then allocate those randomly among all pairs of nodes. Now, what does an Erdos-Renyi network look like? Here I've taken 20 nodes and I've added some edges at random to connect them, the very definition of an Erdos-Renyi random graph. Last week I said that if you apply a spring layout algorithm to a network to reposition the nodes, placing the ones that share an edge close together, this can reveal some of the underlying structure, like hopefully you saw with your or my Facebook network, right? You should have seen interesting communities. However, by definition, the Erdos-Renyi random graph doesn't have interesting structure hidden because the connections are random. So typically when you look at such a network, you're going to see a hairball. Here it's a small hairball. Larger networks, you see a larger hairball. But one thing that is clear and elegant is the degree distribution, which you can derive mathematically, and I show this in greater detail in the mathy version of this lecture. But basically, each node is going to look at n minus 1 other nodes in the network, and it's going to flip a bias coin. With probability p, it's going to have an edge to that other node. With probability 1 minus p, it won't. And we have then the degree distribution, which tells us for every degree, what is the probability that a node has this given degree. And as we increase the probability from 5 to 20%, we can see the degree distribution shifting to the right. That is, the higher the probability of adding an edge, the higher the degree is that a node is likely to have. And this binomial distribution then is very well approximated by the Poisson, as long as you have a largish network and the value of p isn't too high. Now let's look at a NetLogo simulation of the Erdős-Rényi random graph. As I discussed already, there are just a few parameters to set. We have the number of nodes. Here I've chosen 200 nodes. And we can decide whether we want to set the probability of any two nodes being connected or the average number of edges or number of neighbors per node. Here I'm going to select the probability. And I use this slider to adjust the probability, starting out with just a 0.2% probability of any two nodes being connected in this 200 node graph. I click the link, I can do the layout, and what we see here at average degree 0.3 is that we have many isolated nodes, so degree 0 is the most common degree, and a few dyads, even one node having 3 neighbors. Let's see what happens as we up this probability, maybe to 0.5%. Now we see that the components are growing. We can increase this further, maybe to 1%. And we can observe what happens to the average degree. Let's just pick one more value, maybe 2%. And we should be seeing a denser and denser network. You can try and tease this apart a little bit by adjusting the spring length and upping the repulsion force, just to see a little bit more of the internal structure. However, these Erdős-Rényi random graphs, once they're dense enough, really do look like hairballs. What the degree distribution tells us is how evenly distributed the edges are among the nodes. What is the probability that a node has degree 0, degree 1, degree 2, and all of those probabilities have to sum to 1. And by looking at the shape of that distribution, we can tell whether nodes tend to have approximately the same degree with some random variation, or whether perhaps there's some outliers that have degree much higher than others. So to test your understanding, if you have a network of size n, meaning there are n nodes, any one node can have a maximum of n minus 1, or n over 2 edges. And just assume that this is a simple graph, meaning that there aren't multiple edges allowed between the same pair of nodes. Now that maximal degree, which is incidentally n minus 1, is not often achieved in an Erdős-Rényi model. If you have some moderate probability of edges between the nodes, here we'll set it to 20% in a network of 50 nodes, what you'll see is that there is some variation in degree, but the maximum degree, 16, is not that different from the average degree of 10, and it's nowhere close to 49, the actual maximum degree. Now, of course, we can vary the parameters, so we can up that probability to be 0.9. That is 90% of pairs of individuals are acquainted in this network. And now you do have several individuals having the maximal degree, but that maximal degree is not that different from the average. So in an Erdős-Rényi random graph, the degrees of the nodes tend to be pretty similar. You don't have one node having degree 49, and we might call that node a hub, and everyone else having degree 1 or 2. So, to further deepen your understanding, I'd like you to figure out what the approximate average degree of a graph with 100 nodes is, where the probability of any two nodes sharing an edge is 0.04. And I just want the approximate value. Is it 1, 2, 3, or 4? And one final quiz for this segment. Going back to the NetLogo model, I would like you to pick some probability of two nodes sharing an edge, and it's your choice, but I'd like you to keep it constant. And then I'd like you to vary the number of nodes, starting with a small network, generating that network, and then increasing the size of the network, the number of nodes, while the probability stays constant, and then answering the following question. Does the average degree stay the same, increase, or decrease? What insights did this exploration of the Erdős-Renyi random graphs yield? Well, we saw some things which we will delve into further about when the average degree is very low, observing many disconnected components. We also saw the absence of hubs. The Erdős-Renyi random graph does not yield networks where some nodes are very well connected while most others are not. And we will explore these kinds of models that can generate such degree distributions in other segments this week. In the previous section, we discussed some of the ways in which the Erdős-Renyi random graph model is not a fit to some real-world networks. In this section, we'll focus on the particular feature of the presence of hubs. These are extremely well-connected nodes that happen to occur in many real-world networks, but cannot be replicated with the Erdős-Renyi random graph model. Let's look at some of those real-world networks. Here is Sun's Java Forum, an online forum where individuals post questions and others will answer them. We see that there are many individuals who come in and ask, so blue denotes primarily asking, and some individuals will primarily answer, denoted in red. The size of the node denotes the degree. So here is a node who primarily helps, and is helping many low-degree blue nodes. There are some exceptions, so here are some blue nodes that have been helped by many others, and this node appears to both be helping and asking questions of others. We'll look at the degree distribution to see how it captures this uneven participation. Here I'm plotting the cumulative degree distribution, which means that, for example, if we look at having degree 10, say you have helped 10 others, this is the red curve, then we can read that there's a chance of 1 in approximately 100 that you have helped 100 or more people. This is what cumulative means. The probability up to here captures the likelihood that you have this degree or any degree that's greater. Now, we see that some individuals have helped thousands of others. If we look at the askers, there's still quite a skew in the degree, but perhaps at most an individual is helped by dozens of others. So, can we come up with such models? Would be good, because this isn't the only network that has such skew. So here is a network of reported sexual partners, and typically men will report having had more partners than women do, but in either case you can see a heavy skew with the majority of individuals reporting having a couple of partners, and then a few individuals reporting having many. When we look at such a power law distribution, you'll notice that I used a log-log scale and that the distributions looked approximately linear on this scale. The reason why I did this is because if you use a linear scale that is not log-log, what you find is that you can't really distinguish, is the probability of having degree 20, is it 0 or is it different from 0?
similarly here for 50, right? It doesn't look any different than 20, which actually looks like, the value is 0. But if we replot this on a log-log scale, what we see is that the probability of having degree 50 is somewhere above 0.00005. Now, this may seem like a very, very low probability, but if you have a network of 100,000 nodes, you would expect actually on average 5 of them to have exactly degree 50. So it's useful to know this because you will actually observe these high degree nodes if your degree distribution is power law. And if you were to just look on a linear scale, you would have this L, which would obscure this relationship. So you typically want to plot your degree distribution on a log-log scale if you're dealing with networks that have hubs in them. On the other hand, when we looked at the Erdős-Rényi random graph, what we saw was a Poisson distribution, which is this approximation to the binomial. And here again, if we look at having degree 20 or having degree 50, these look pretty much like 0 again. And if we actually look up the likelihood that a node has degree 50, it's something like 10 to the minus 26 or 28 or something like that. It is puny. It is actually a true 0. So with an Erdős-Rényi random graph, here you would never see a node with degree 50 when the average is something more like 10. And so these two distributions are actually quite different. So we'll need a different model than the Erdős-Rényi random graph model if we are to explain high degree nodes. This power law distribution, because it's a straight line on a log-log plot, it ends up being a line. So if you take the log of the probability of having degree k, it's going to be equal to some constant minus alpha, this is the power law exponent, times the log of the degree. And if you exponentiate both sides, you get this relationship that the probability of a node having degree k is equal to some constant times k to the minus alpha. Again, this power law exponent shows up. Now let's see if you can answer this. As the exponent alpha increases, the downward slope of the line on a log-log plot, does it stay the same? Does it become milder? Or does it become steeper as alpha increases? Now, as I said, we need a new model. The Erdős-Rényi just isn't going to cut it. And we're going to need two ingredients. The first is that nodes are going to appear over time. If you think about social networks, this could be birth, or it could be someone joining a new workplace or a new school where they approach the existing network and then form social ties. If you're thinking about new publications, the new paper that is published is going to be citing previous papers that are already in the citation graph. So just to illustrate a little bit further, you have an existing network. And here's a node with no connections, and here is a node with 3 different connections. And now a new node comes in, and it has some fixed number of edges allocated with which it will attach to the existing graph. So does it want to attach to this node with one edge and to this other node with another edge? Well, in the preferential attachment model, what we'll see is that the node is going to prefer to attach to the existing node in proportion to the number of edges it already has. So it would be more likely to attach to, 3 times more likely to attach to this node, which has 3 edges, versus this node, which has 1 edge. Let's look at networks that are grown just with ingredient 1. So new nodes will join over time, but there isn't a preference that they have for joining to certain nodes and not others. The only restriction is that they have to link to someone who's already there. So for example, each node might come in with 2 edges. What this means is that by time t, you have t nodes, 1 joined at each time step. It also means that at time t, when that new node comes in with m edges, each existing node is expected to increase its degree by m over t. That is, it's competing with t other nodes in the network for m edges. This also means that over time, the older nodes who have been around longer are going to accumulate more edges just by having been around. So if node I was born before node j, we would expect on average that the degree of node I is greater than the degree of node j. Because this is a random growth process, that need not always be true, but it typically is. So, how could one make the growth model more realistic for social networks? Should old nodes die? Should some nodes be more sociable? Should friendships wane over time? Or perhaps all of the above? I hope you picked all of the above because even though mathematically it becomes more difficult to solve such models, they capture many of the realities of networks. So in social networks, individuals tend to leave one way or another eventually. In citation networks, older papers may lose interest over time, or maybe for the best ones, their results become so ingrained that one doesn't even cite them. It's just known as a general truth, part of our knowledge base. Maybe some nodes are more sociable. Why should everyone have the same number of edges? Maybe some individuals form more ties simply because of an intrinsic property. Friendships might wane over time. Why do you have to keep all the edges you had in different contexts from a long time ago? And you can probably think of many other ways in which you can enrich such models. Now let's turn to the second ingredient, which is that of preferential attachment. Here, we're going to, when the new node comes in, it's going to want to connect to the popular kid and not to the less popular kid, or the loner. And this process is also known as cumulative advantage or rich get richer or the Matthew effect, meaning that if you already have a lot, you're going to get even more. And here we're talking about edges as being the wealth. This model was first introduced by Price, who was modeling how papers get cited, and it has been observed for a long time that some papers are just cited a whole lot more than others. And here, rather than having the probability of attachment directly proportional to the degree, it's going to be proportional to the degree plus 1, which is going to take care of a cold start problem. And that is that if a node has degree 0, it would mean that in proportion it would never get cited. Of course, this isn't the case. Papers, all start with 0 citations and then eventually accumulate them. This kind of process will give you a power law exponent alpha of 2 plus 1 over m. And this tends to be in good agreement with many of the observed empirical distributions. Just to look at this image again, so we have a new node coming in. It could cite the paper that hasn't been cited at all, or it can cite the paper which has lots of existing citations. And it's going to prefer to cite to this one in greater proportion than this one. How does this actually happen? Well, there could be many underlying mechanisms, but one of them is copying. So if you're reading one paper, you might actually look through its references and find that it cites another paper. And so you copy the citations of others. And because that existing paper you're reading is more the paper that it's citing has higher degree by virtue of the fact that it's being cited, you're then more likely to cite it as well. So it's a cumulative process. It may also just be that more highly cited papers are just more visible when you search in different databases. It may show you the more highly cited papers first, which again would give such papers an advantage. The more recent and very widely known model is the Barabashi-Albert model, which was first used to model the degree distribution of the World Wide Web. And in particular, Laszlo Barabási and Rekha Albert were looking at the Notre Dame website and noting that some of the web pages had many more edges, that is, links, than others. And they considered an undirected model, even though in reality the web is a directed graph. So the process is going to start with some initial subgraph. It could be a fully connected clique of a few nodes who all link to each other, or maybe it is just a circle. And each new node is going to, again, come in with m edges, and the probability of connecting to node I is going to be proportional to the degree of node I. That is, it's going to be proportional to k sub I. And this is going to result in a power law with an exponent alpha of 3. 3 is a bit high for, it's a bit higher than most of the observed power law distributions. However, one can modify the model in interesting ways. For example, giving the nodes different fitness or some intrinsic attractiveness, such that you might prefer certain nodes even if their degree initially is lower, and this will produce more realistic power law distributions and exponents that are closer to 2 than they are to 3. But let's see what it looks like with the pure Barabási-Albert process. After a while, you will see some hubs emerge. Here the nodes are sized in proportion to their degree. And we can contrast this with the random growth. Even with random growth, we had some nodes, typically the older nodes, who had higher degree, but there wasn't as much of a disparity between the best connected nodes and the least well-connected nodes as there is in the Barabási-Albert model. So again, this is the preferential attachment and random attachment, and both have the same growth mechanism in that nodes join one by one over time. So just to review, we have the properties of the Barabási-Albert graph, a power law exponent of 3. We have that the graph is connected because we start out with a connected graph, and every subsequent node is going to attach to an existing node which itself has attached through some chain to some of the original graph. We also have that the older here are richer, and if you track the average degree of a node born at time 5 versus one that was born at time 100, that node that joined later, it's going to have a really hard time ever catching up to the node that had the advantage of being there early. Now, this is not entirely realistic either. If you look, for example, at the oldest websites, some of them are still around and popular, but many of them never got a huge following, and that is because over time there's some fitness to the different nodes. Some websites grow very, very popular and others wane in popularity, and it's not all about how many existing edges they have. Next, I'd like you to explore these growth models yourself. Let me find the NetLogo model. What you're going to do is you're going to start out with just 2 nodes which share an edge, and you have this slider, which is the probability that a new node which comes in is going to attach preferentially in according to the degree of the existing nodes, or maybe it's just going to attach at random. So let's first start with random, and I'm going to click go, and this is going to be a little bit slow, so I'm going to speed it up. Maybe stop once we have about 250 nodes. So there you go. You have the degree distribution both on a linear scale and on a log-log scale. And you also have the ability now to change to preferential attachment. I'm going to set up and say go and stop at a similar Number of nodes, 250, and hopefully already visually you can see that the structure is different. You can see the hubs here. You can also see the difference in the degree distribution. So going back, we have our next quiz question, which is relative to the random growth model, the degree distribution in the preferential attachment model, does it resemble the power law distribution less or more? Hopefully you got that it actually is more power law than the random growth model, which tends to have an exponential cutoff. And we know that actually this should match the Barbashi-Albert model and that the exponent is 3. The power law exponent is 3. However, it's difficult to tell that from the NetLogo graph, but there are ways of fitting such distributions and deriving the exponent, which is something that I'll cover in an extra advanced segment next week in case you're interested. So to summarize, we talked about growth models because networks aren't born, they're made. They evolve. Nodes are added to the network. Edges are added to the network. And we saw a couple of properties of these very basic growth models. The first is that because nodes join over time, if a node is older, it's more likely to have accumulated edges. But the true hubs you get when you have preferential attachment. That is, it isn't enough for the node to just kind of lie back and wait for edges to come in. The new nodes have to prefer a well-connected node. So for example, a new kid joining a school will want to hang out with a popular kid as opposed to the loner. Or a new paper will want to cite the well-cited paper as opposed to some other paper that hasn't been cited at all, or it might do so accidentally, not accidentally, but it's reading another paper, and so reading through those citations, it's going to end up copying some of them and so citing already well-cited papers. Okay, in any case, once you have this kind of preferential attachment, you're going to have the formation of hubs. Now, in this week's assignment, I've left a lot of the fun kind of out of the lecture and put it into the assignment. So even if you're just following the lectures without taking the course for credit and you're not doing the assignments, really you should do this assignment because it's going to show you why modeling is important. That is, we're going to look at these different models and you're going to be able to tell what the effect of the different growth mechanisms is on the ability for an infectious agent to spread. So this infectious agent, it could be a bacterium, it could be information, and you're going to look at different aspects. So the first is going to be the distribution of component sizes in the network and how this impacts how far the virus, for example, can spread. The second thing you're going to look at is in growth models, whether the growth is random or preferential, whether that impacts the speed with which the infection can spread. So I think that actually is like kind of the other half of what we should be learning this week, which is not just that these models can explain the structure of the networks that we see around us, but that having these models, we then gain insight into how different processes might then occur differently depending on how the network grew or came to be. So I hope you will find that fun, and I'll see you next week.